All right, so this is Math313, lecture 22, I believe. And so what we're now doing is we're now moving on to chapter 8. So I deliberately have not told you to read chapter 8 for class today so that you can be thinking about a lot of these problems live on the spot. You know, how would we attack something like this? Okay. So the idea is to look at what's called Diophantine equations. So what we're looking at is, equations with integer coefficients, integer powers, and looking for integer or rational solutions. So can someone give me an example of an equation with integer coefficients, integer powers that we've seen before in this semester, or that you've seen in another class, or that you've read about? X equals 0. Okay? That is a Diophantine equation. Unfortunately, we don't have time today to get into how you would solve this one, so I will have to leave this as an exercise. Any other Diophantine equations we may have seen this semester, or that you've heard about, that are famous? From Maslow's theorem. X to the n plus y to the n equals z to the n, with x, y, z not equals 0. Another one we've done is the cookie problem. X1 plus xp equals c. Then there's Waring's problem, x1 to the k plus xs to the k equals n. For what values of n can you write it as a sum of s perfect kth powers? And the reason we often say perfect kth powers and not kth powers is so I don't have s kth powers and you're wondering, are you multiplying s and k? It's really just done for the sake of how we present things, how we say things. So these are all examples of Diophantine equations. And we want to find out, are there any solutions? Are there solutions in the integers? Are there solutions in the rationals? And if so, how do we find them? Later on, we might look at some elliptic curves. We've seen some examples in RSA. Looking at E times D, E is congruent to 1 mod phi of PQ. So now we've got a mod 1 here, so it's a little bit different, but you're still trying to find something like this. So we could easily get rid of this by, instead of saying it is congruent to 1 mod PQ, we could have said it equals 1 plus, maybe n p minus 1 q minus 1, and give ourselves a third variable, and view this as an equation in 3 variables, e, d, and n. So we could convert this to a form like this. It turns out it is an extremely difficult problem figuring out when a Diophantine equation has a solution. It is highly non-trivial. So the question is there any easy ways you can think of to try to find out maybe if it has a solution or not? Maybe any simple tests? Maybe a way to show that it doesn't have a solution. Maybe if something holds, there won't be a solution. So, technically not a, is that a call or? It's not a call. All right, so let's consider 1701x plus 24601y equals 31415,926. Do you think there's a solution to this? Yes?
Well, if 1701 and 24601 are relatively prime, then there should be.
Ah, good. So if they're relatively prime, this should be. And if they're not relatively prime?
Then if
Well, so we know everything here. We get all multiples of the GCD of 1701 and 24601. I can get any multiple of the GCD. And so all we have to do now is figure out what is the GCD of 1701 and 24601, and does that divide 314,15926? And if it does, then we have a solution. If it doesn't, we don't. And at this point, I've lost interest, because now it's just a really straightforward calculation. How would we find the GCD of these two numbers? Euclidean algorithm. So just use Euclidean algorithm. What about 2004x plus 1986y equals 1701? No. Why not?
Because the GCD is at least 2.
So you got to be careful, not at least 2. The GCD is at least a multiple of 2. 2 divides the GCD. I'm sorry? Well, no, but I'm saying if the GCD was 3, it could be possible. So over here, we know the GCD is a multiple of 2. So there's no solution. So there's another way of looking at this. The way of looking at this is, rather than calculating the GCD, what we can do is, instead of trying to solve this over the integers, we can try to solve this over another set. What set of numbers do you think I want to solve this over?
Rationals?
Not rationals, because rationals is more expansive than the integers. So I want a smaller set than the integers. Not naturals. Not evens. Not odds. Those are still infinite sets. There's a really nice finite set, Z2. Study over Z mod 2Z. If there's an integer solution, will there be a solution when we reduce both sides mod 2? Yes. If there's no solution, then there can't be a solution over the integers. So more generally, study mod p for a prime p. If no solution, no integer solutions to the original problem. And if you want, you could even study mod p to a power. What if you have a solution for every prime? What do you think should be true?
There's a solution.
Yeah, I mean, doesn't that seem like, if you can solve it for every prime, you should be able to piece together a solution. So this would be a great hope, or conjecture. If solution for all primes, then solution over the integers. If you were to make the laws of calculus, what would the derivative of a product be? Yes. Product of the derivatives. If you were to make the laws of calculus, what would the derivative of quotient be? Derivative would be the quotient of the derivatives. A lot of times what we want is not necessarily true. So the question is this going to hold? Will there always be a solution of the integers? Is there some way to piece things together? So in chapter 8, they go through a lot of different cases. There are 2 examples that are usually known. The first one I hadn't seen before. So consider x to the 4th minus 17y to the fourth equals z squared. Or consider 3x cubed plus 4y cubed plus 5z cubed equals 0. What do you think is probably true about each of these equations? Yes?
They probably don't have solutions of the integers.
They don't have solutions of the integers, and given that I'm writing them on the board right now, yeah, so they have solutions for all prime, but no integer solutions. Quite sad. So what that means is that this conjecture, this hope, can't be true in general. It's too much to assert that given any Diophantine equation, if it has a solution for every prime, then you can somehow build up a solution. So we need to lower our sights. So when you look at this, what's the first thing that comes to mind when you look at these equations? Yeah.
They all have 3 variables?
They all have 3 variables. So maybe one of the issues is that this has too many variables. That if I restrict myself to at most 2 variables, maybe it's the case if I always have a solution over the primes, I will have a solution. Well, let's see. If I so there's no way to immediately, I think, go from something like this to just 2 variables. Well, what if I just take maybe z equals 1? We don't know if it's going to be the same z mod each different prime. So maybe if we restrict ourselves to just 2 variables, things will work. So that's one issue in looking at this, is that maybe 3 variables is too many. Maybe the hope is true if we only have 2 variables. What else might you notice when you look at this? So one thing is the number of variables.
Power's greater than 1.
I'm sorry?
Power's greater than 1.
Power is greater than 1. So maybe if the powers are too large, there's a problem. So maybe the hope works if the powers are sufficiently small. So for instance, if the powers are only 1, maybe we can always get a solution. Maybe if the powers are only 2, we can get a solution. So the question is, would you be able to get a solution if the powers are just 1? If you allow yourself to work in rationals, yes. It's not hard to get a solution if you work in rationals. So we'll talk a little bit more about this later. What I want to do now is I want to talk a little bit about constructive ways to try to find solutions. So the book goes through 2 different approaches. The first approach is to take an equation and solve it mod a prime. And then solve it mod the prime squared, the prime cubed, the prime to the fourth, and you try to build up a solution. And this leads to a lot of nice stuff in algebraic number theory, where this leads to what's called the p-adics, and the p-adics behave very strangely. The higher the power of a prime you are, the smaller you are. And so we'll talk a little bit about that on Friday. But I wanted to just go back to something you've probably seen before. You haven't listed it yet when I was asking for famous Diophantine equations. There's a very famous Diophantine equation that involves no more than a squared power. The Pythagorean theorem. X squared plus y squared is z squared. So we know some solutions, right? Somebody give me a solution. 3, 4, 5. Give me another non-isomorphic solution. I'm not going to consider 6, 8, 10, because that's just multiple. 5, 12, 13.
7, 24, 25.
So how do people know how to find all the solutions? Yes.
At least I know where to find a lot of them.
Okay.
I don't know if it finds all of them, but if you just go to an odd number, square it, and then that's because and since you know the difference between any 2 consecutive perfect squares is 2n plus 1.
Mm-hmm.
You can just set that equal to the odd number squared.
Okay, so what you try to do is you're trying to look at numbers of very special form, and you'll be able to find an infinite family. Yes. So one way is to try to look at very special values of some of the variables. And so if maybe x and z are adjacent squares, and you look at the difference is going to be maybe 2n plus 1. If 2n plus 1 itself is a square, then you'd be fine. So that's one way to do things. So that would give you infinitely many solutions, but it may not give you all the solutions. So has anybody seen how to find all the solutions for this? Okay, so I thought that this would be a nice problem as just like a warm-up to Chapter 8 to finding solutions. This is something that could have been done when you learn the Pythagorean theorem, but it's always interesting to see what teachers choose to present or not. We proved the Pythagorean theorem in this class, right? Have we proved it in this class? We haven't proved the Pythagorean theorem? How many of you could prove the Pythagorean theorem right now if your life or grade depended on it? All right. Given that not every hand is up, there are certain things that you should know if you're going to graduate as a math major. You should know the square root of 2 is irrational. You should know analysis is better than algebra. And you should be able to prove the Pythagorean theorem. So I will do a brief detour right now, and I will prove the Pythagorean theorem just because this is such an important result. You should not be able to graduate as a math major without being able to prove the Pythagorean theorem. This is how we measure length. It's one of the most fundamental objects we looked at. So I will give 2 proofs, and then one U.S. president stands out among all presidents in U.S. history. Anybody know which president I'm thinking of? Garfield. James Garfield. He did something that no other U.S. president has ever done. He did go to Williams, and no other U.S. president has been able to go to Williams. Died coming back to his reunion, which is why I was a little concerned when I was hearing talk about planning reunion events. So just please be careful, because that's how we lost Garfield. But Garfield has something credited to him. He has a proof of the Pythagorean theorem credited to him. So I will send some links on this. So here's my 2 favorite proofs. So let me just do this right. So let's call this A. Let's call this B. I'll try to draw it off to the scale. A, B, A, B, A, B. So if I've done this right, this should be a square over here with sides of length C. And now we just calculate the area 2 different ways. So the area of the big square is A plus B squared, and it's equal to C squared plus 4 times 1/2 AB. And we assume at this point that we know that the area of a rectangle is length times width, and a right triangle is half of a rectangle, so it has half. So now when you expand things out, you get A squared plus 2AB plus B squared is C squared plus 2AB. We cancel the 2ABs, and there's Pythagoras. All right, so that's one proof. The other proof, which I like, introduces a really nice concept. So imagine I have a right triangle and an angle theta. I claim the area must be of the form some function of theta times c squared. The first is, if you know trigonometry, this is going to be c sine theta, this is going to be c cosine theta, so the area is going to be c squared, 1/2 c squared sine theta cosine theta. The other thing is, this is an area. If I increase c by a factor of r, I increase the length and the width by a factor of r, so the area increases by a factor of r squared. So the area has to be proportional to the square of the hypotenuse. And I'll just call that proportionality constant theta. Okay? All good geometry proofs at some point involve drawing an auxiliary line. And given that we are doing things about right triangles, we probably want to draw an auxiliary line that involves a right angle. So the best auxiliary line is to draw the perpendicular to the hypotenuse. And now I have three triangles, and the two small triangles are similar to the large one. So if this is theta, this is 90 minus theta, so this angle here is theta. So I will give the triangles the boring names of triangle 1 and triangle 2. And so the area of triangle 1 plus the area of triangle 2 is the area of the whole triangle. What's the area of triangle 1? It's f of theta times the hypotenuse squared, which is a squared. The area of triangle 2 is f of theta times b squared, and this is f of theta times c squared. So now what do we do? Yes? Divide by f of theta. But we are not physicists. So what do we need to do before we can divide by f of theta? So what do I have to do before I can divide by f of theta? So I can factor out the f of theta, and then I want to divide both sides by f of theta. What do I have to check before I divide by f of theta? Make sure it's not 0. So if f of theta is 0, then the triangle would have 0 area. So as long as my angle is not 0 or pi, I won't have 0 area. So I can divide by f of theta, and I just get a squared plus b squared is c squared. So what I like about this proof is this is dimensional analysis. You can use dimensional analysis to figure out a lot of problems by trying to figure out what are the fundamental things that are in play. And so the example I like to give is, imagine you have a pendulum swinging. You have mass in kilograms. You have the acceleration due to gravity in meters per second squared. You have the length in meters, and you have an angle in theta. If I want to calculate the period, which is in seconds, that's how long it takes to either go back or back and forth. I want to look at how can I combine these objects to get a unit of seconds. Well, since this is the only object that has kilograms, if this is in play, there's no way to cancel the kilograms. So the mass of the bob can't come into play. So I've got theta, L, and G. If I look at L divided by G, that's seconds squared. So the period has to be some function of theta times the square root of L over G. So before you do any experiments in the lab, you can already see that the motion of the pendulum, if you quadruple the length, you should double the period. It's nice. I mean, I have given entire lectures on dimensional analysis. It's one of the most powerful techniques we have. You want to get a sense of what matters. Now, the fact that this is a constant and doesn't depend on theta, that's hard. Because I can't use anything from dimensional analysis to sniff this out. But the fact that it depends on the square root of L over G, that's really nice to be able to look at a problem and get a sense of what it's like. I'm trying to think. No, I did that in problem solving class, but there's other stuff we can do on dimensional analysis. If people are interested, send me an email. I'm happy to work some stuff on this. It's related to some stuff we might do on elliptic curves. All right. This was a small digression, but I can't let you graduate without seeing Pythagoras. And I guess the last thing, just so I won't veto your graduation, is you need to know, and I think we've done this before, that I squared is the square root of -1. All right? I can't think of anything else that would prevent me from saying you deserve to graduate.
I is the square root of -1?
Sorry, yes. Sorry. If you say it the other way, either you don't deserve to graduate or I don't deserve to be your teacher, one or the other. All right. So these are just some basic math facts you should know. All right. So now let's go back to the Pythagorean theorem. So now we know that this is true for right triangles. Instead of studying this, we could study u squared plus v squared equals 1, where u is x over z and y and v is y over z. So we've reduced it from having 3 variables to having 2 variables, but now instead of studying things over the integers, we're now studying things over the rationals. The only thing we have to be careful about is, of course, we can't divide by 0. Is there a danger that z could have been 0? Is there a solution to this when z equals 0? Yes. We have the 0, 0, 0 triangle. 0 squared plus 0 squared is 0 squared. So we do lose one solution when we do this. This is not a difficult solution to remember. Or we could say we only care about non-trivial solutions where all the variables are non-zero, or at least one of the variables is non-zero. So anything like that, and now we can study u squared plus v squared equals 1. Okay, what kind of shape is u squared plus v squared equals 1? It's a circle. And so, not perfect, but not a horrible circle. Okay, so here is u squared plus v squared equals 1. And we want to find all the rational points on the circle. So we would have the point 3/5, 4/5. We'd have the point 5/13, 12/13. We would have the point 7/24. 7/25, 24/25. How do we find all the different points? So what we're going to do is we're going to parameterize our solution space. And what I'm trying to do is, since I know some of you are working on the exam, is I'm trying to keep to a minimum the amount of reading you need to do this week so that you have plenty of time to be doing the exam, and just choose material that I can present without you having to do too much at home. Have you seen the word parameterize before in any of your calculus classes? Which one? Multi. Sometimes you talk about parameterizing a curve. You often talk about parameterizing a curve so that you walk along it at unit speed, because this way you don't have to remember, oh, do I have to divide by the length of v prime or the length of v prime squared? If the speed is always 1, it doesn't matter if you're supposed to have that factor. So the way to parameterize the solutions is, if you know one solution, it turns out you can find infinitely many. Do we know any solutions to x squared plus y squared equals z squared? I'm sorry, to u squared plus v squared equals 1? We've got 3 on the board. It turns out none of these are popular solutions. So if you were to ask a younger child to solve u squared plus v squared equals 1, what solutions would you get? 0, 1, and 1, 0. Turns out that we don't want those solutions. There's another solution. It's close to that, yes.
1 over rad 2, 1 over rad 2.
Nope. That works. That works. But we don't want that. It's close to 1, 0. It's really close to 1, 0. So you were solving by setting v equal to 0, and you got the point 1, 0. What's the other point?
0.
I'm sorry?
0,
1. No, because I'm setting v equal to 0. So when v equals 0, I get 2 solutions. I get 1, 0, negative 1, 0. So it doesn't matter if we do negative 1, 0 or 1, 0. The convention is to always give this lecture with negative 1, 0 as the solution. And so this way we will match what's in other books. So we will always start, here is one solution, negative 1, 0. It doesn't matter. How many of you have taken economics? Okay. What are the labels?
Price and quantity.
Yeah, which one goes where?
Price on the y-axis.
So price goes on the y-axis. Which one is supply, which one is demand? Supply goes up, demand goes down, right? So as the price of a quantity increases, suppliers are willing to produce more and more and more. Do you have to put price on the y-axis? No. But if you don't do this, your notation will not match all other notation. Unfortunately, in mathematics, we often have choices. And frequently, the mathematicians and the physicists will have different choices in terms of how they do spherical coordinates or how they normalize certain functions. And you have to be careful and check. So whenever possible, it's nice to use the notation everybody uses. Anybody following the United Airlines story right now? Anybody know how much United stock has dropped? I've heard over $200 million.
But it bounced back really quick.
Yeah. How much did it bounce back?
About like 60 to 80% of how much it dropped.
Yeah, I mean, it was interesting to think, is this a time to have just quickly invested in United? Because the company is, still essentially what it was before. But there was a really great article that United's mistake was they should have just kept upping the reimbursement until they reached the point where somebody will say, I'll take it. And it's the first one to say, so I don't know, for those of you who hadn't heard, United was forced to remove 4 people from a flight because they needed to make sure a flight crew got to a city for the next morning. And one person did not want to leave and was physically removed from the plane and somewhat injured. And he did not want the compensation that they were offering. If they just keep increasing the compensation, eventually it reaches the point where someone will say, I'll take it. And then they would have avoided a lot of the bad publicity. So over here, we just want to match our notation with everyone else's. Everyone else seems to use -1, 1, so we're going to use that. So imagine we now have some point over here, UV. We can draw the line connecting them. And let's say UV is a solution with rational coordinates. What can you say about this solution? Or what can you say about the line?
It has
Rational slope. So line has rational slope and rational intercept. So if you give me any point on the circle and I draw the line connecting, this line is going to have a rational slope and a rational intercept. What's the definition of the intercept? What's the definition of the intercept of a line?
when x equals 0, what the line?
So it's your y equals mx plus b.
So it's the b part.
So it's the b part. So now, what if I give you a line with rational slope and rational intercept? What could you say?
Then it should intersect the circle at rational.
So hopefully it would intersect the circle at a rational point. And again, we could write the line 2 different ways. We can write it so that we're talking about its y-intercept. We could talk about it so it has the x-intercept. Right, when you're writing the equation y equals mx plus b, you could also write x equals my plus b. In that case, it's much easier to see the intercept is rational here. I'm forcing it to be rational by having it go through -1, 0. So the idea is we're trying to find a way to search through the whole space. And it would be wonderful if what we could say is, you give me a rational slope, and I'm going to hit a rational point. And every point corresponds to a rational slope. Is it possible that there could be 2 different lines going from here to a rational point? No. 2 points uniquely determine a line. So the idea is that we can hopefully go through the space in a one-to-one manner, and that every rational number, every rational slope, will correspond to a different point on the circle. So let's try to see what happens if we make this rigorous. And so the problems get a lot more involved when you go from studying Pythagoras to studying elliptic curves, but the general idea is the same. So given -1, 0, and a rational slope, what letter do you want to use for the rational slope? There are 2 acceptable choices. R, which is what I would do, even though it's a little bit tough as a Bostonian. What's the other letter you could use for the slope? Yeah, I guess you could use S, but S is a horrible letter to use. Because whenever you use an S, you've got to be very careful about S's looking like 5s. And so if possible, you avoid using S. When you study the Riemann zeta function, you have no choice. You must follow Riemann's notation. But if I can avoid using S, there's another common letter we often use for slope, M. That would also be acceptable. I like to use R here to remind myself I'm looking at something that's rational. You know, again, the equations today are not going to be that bad. The point is to try to develop good habits so when things do get involved, you can quickly glance at an equation and see what's going on. Okay, so let's imagine we have, here's the point, -1, 0, and we have a rational slope of R. And so we want to find the equation of the line. So imagine we have some arbitrary point xy on the line. Then we get y minus 0 over x minus -1 is R. And that's how we would get the equation of the line. Because if xy is on the line, it's got to give us the slope of R from the point. So then this just becomes y equals R x plus 1. So this line is going to hit the circle of radius 1 at some point uv. And so we know two things. We know u squared plus v squared is 1. And now, since we know this, we know v is equal to r u plus 1. So we want to solve this simultaneous set of equations. This is unfortunately not something that we can do using linear algebra because we now have squares over here. So when you look at these equations, what's your first thought? Yeah, I mean, my feeling is I've got v really nicely written in terms of u. Let me substitute for v squared. And so if I combine these, I get u squared plus r squared u plus 1 squared equals 1. All right, now what do I do? Yeah, expand. So when we expand this out, we'll get u squared plus r squared u squared plus 2r squared. I'm sorry, this is a u, yes, u plus r squared equals 1. So we get 1 plus r squared u squared plus 2r squared u plus r squared minus 1 equals 0. Now what do we do? What do we do now? How do we do that? Not the binomial, the quadratic formula, right? So the hope is this is going to give us a rational number. Why might you be a little concerned at this point? We're about to use the quadratic formula. No, it doesn't always give rational solutions when you have a polynomial with integer coefficients. You've got square roots. So I'm really hoping things are going to cancel. Well, we've got a 1 plus r squared, we have a 2r squared, we have an r squared minus 1. It actually does look a little promising in terms of how things are going to go. So we get u is equal to negative b, so it's negative 2r squared plus or minus the square root of b squared, 1 plus r squared squared minus, I'm sorry, that's not b squared. B squared is going to be 4 out of the 4th. Minus 4ac, so it's going to be minus 1 plus r squared minus 1. Well, with the r squared minus 1, why don't I just pull in the minus sign and make this 1 minus r squared? 1 minus r squared all over 2a, 2, 1 plus r squared. So the only issue is the square root. Well, we have a 1 plus r squared, 1 minus r squared. That becomes a 1 minus And I forgot a 4 because it's 4. So this becomes a 1 minus r to the 4th. We've got an r to the 4th over here. They perfectly cancel, and we're left with the square root of 4. Square root of 4 is just 2. So we get u equals negative 2r squared plus or minus 2 all over 2, 1 plus r squared. All right, we can cancel the 2's, and we get negative r squared plus or minus 1 over 1 plus r squared. Does that answer look reasonable? So what check can you do to see is this reasonable? Yes?
Is negative 1 a solution?
So one thing is to check is negative 1 a solution. So if I take r to be 0, I will get negative 1.
Well, also because we're trying to solve solutions where it intersects the circle.
Right?
Negative x equals negative 1 should always be a solution no matter what the value of r is.
Mm-hmm.
Yeah, and which it is. Because
Right. So if I look at r squared plus 1, I'm sorry, if I look at r squared minus 1 over 1 plus r squared, I'm going to get negative 1. So the roots are u equals negative 1, and then the new root is going to be the plus 1. So it'll be 1 minus r squared over 1 plus r squared. So this is good because we forced negative 1, 0 to be on the line and the circle, and it's on the line and circle. Good. And then the other one we get is 1 minus r squared over 1 plus r squared. Does that look reasonable to you? What smell test does it pass?
it's rational.
It's rational. But there's another test. How big is this number?
So less
It's less than or equal to 1. Right? It's supposed to be on the unit circle. I should not be getting an x-coordinate less than or equal to 1. So this, still a solution. And the absolute value is less than or equal to 1. So again, whenever you have an answer, if you can do any simple tests, that's really useful. Okay, so now, I was afraid it would not move. So we'll try again. Let's see if I walk this way. All right. So let's go back to what we had before. I hit it too hard. Long day. So let's go back to what we had before. So our goal was to come up with all the solutions to the Pythagoreans. And now we've just shown that you give me any rational slope, and I get a point on the circle. And any point on the circle with rational coordinates, and any point on the circle with rational coordinates corresponds to a rational slope. There's a one-to-one correspondence. So we now have all the solutions. So u is equal to 1 minus r squared over 1 plus r squared. And what will v be? V is just r times u plus 1. So when we have u plus 1, so here it's going to be r u plus 1. So when I add 1 to this, I have to add 1 plus r squared over 1 plus r squared. The r squareds cancel, and I think we get 2 over 1 plus r squared. So when you simplify, this is 2u plus 1. It's 2r over 1 plus r squared. And as a check, u squared plus v squared is 1 minus r squared squared over 1 plus r squared squared plus 4r squared over 1 plus r squared squared. And we get 1 minus 2r squared plus 4r squared. So it's going to become 1 plus 2r squared plus r to the 4th over 1 plus 2r squared plus r to the 4th. It does work. So here are all the solutions u and v. Well, we originally didn't want solutions u and v. We wanted solutions x, y, and z. Well, now we can get x, y, and z. So x is going to be 1 minus r squared. Y would be 2r. And z would be 1 plus r squared. So if you do anything like that, this will be a solution. And so this is a way to parameterize all the solutions with some free rational parameter. And then, one of the issues could be maybe R has a denominator. Or in fact, almost surely R will have a denominator. This number will be less than 1, so I could rescale things. If R equals P over Q, or R equals M over N, I can multiply through and I can clear the denominator. So let's just end with, how we would, could you just hit the, thank you. So to just quickly clear it, let's say R equals P over Q, the most general thing. So, X is 1 minus R squared, Y is 2R, Z is 1 plus R squared. So now if I multiply through by, which I multiply through by, I think maybe Q squared. So then, Q squared X, Q squared Y, Q squared Z, and then I would get Q squared minus P squared. I would get 2 P over Q times Q squared is 2PQ. And then over here I would get Q squared plus P squared. And when you look at this, if I square this and add this, this is now going to change the minus cross term to a plus, and everything's going to work. And so this is really all of your Pythagorean triples. So we are able to come up with an explicit formula that will list them all. We're parameterizing them with one free parameter, the rational slope. And then next time we'll talk about how we would extend this to do more complicated things like elliptic curves, and we'll talk a little bit about how you would try to do expansions in terms of primes and prime powers. So we've got about 2 minutes left. This is not enough time to start a new topic, but I will end with just one question about slopes. I'm just curious to see what people remember. It doesn't seem to want to move, so I will just work in this part of the board. So let's say I have two lines that are perpendicular with slope m and slope m prime. Does anybody remember the relationship between m and m prime? Yes.
M prime is equal to -1 over m?
Yeah. M prime equals -1. So this is a nice exercise to prove this. So I'll make this extra credit. How would you prove that the product of the slopes is -1? Now, of course, there's something that's fascinating that goes on here. This actually gives us infinity times 0 equals -1. Why? If I take the x-axis, what's the slope of the x-axis? What's the slope of the y-axis? Plus infinity. So if I deform it slightly, the product of the slopes is -1, -1, -1, -1, -1, undefined, -1, -1, -1, -1. So the limit should be defined to be -1. So this is actually a situation where we would interpret infinity times 0 is -1. This is why the standard rule is whenever you have infinity times 0, this is undefined. It can be so many things depending on the problem. We never want to add infinity with negative infinity. We never want to multiply infinity by 0. And so as a nice extra credit, prove this. Okay, so this is a good place to stop. Enjoy the rest of our new spring.